Okay, we say carbon likes to have how many bonds? Show me in the chat. All right, and so number of bonds, lone pairs,
Recording in
charge. Okay, where's this? Cool. So when carbon, we say it likes to have 4 bonds, no lone pairs. And when we say likes to have, that means it has a formal charge of 0. Okay, so first of all, carbon with like 5 bonds. Whatever. Bottom line, never going to happen. As soon as you see a carbon atom with 5 bonds, it should make your organic chemistry brain hurt. All right, it's just never going to happen. If carbon has a formal charge of -1, you will see that, and this is, so first of all, real quick, atoms don't like to have formal charges. If they do, they're kind of like a higher energy species. Nonetheless, it turns out that we see these a lot of times in chemical reactions, right? So something like oxygen with a positive charge, does it want to have that positive charge? No, it will only exist for like 0.1 seconds, but it might be an important species that's like driving a chemical reaction. So same thing with carbon. When we're talking about carbon with a formal charge, it's not very stable, but nonetheless, we'll see them as intermediates in chemical reactions. So what carbon with a formal charge looks like, formal charge of -1, is it has 3 bonds and a lone pair of electrons. Okay, that's carbon with a formal charge of -1. That does not violate the octet rule. You can kind of convince yourself that carbon still has 8 electrons in its octet, 2, 4, 6, 8. The weirder one, and one that's actually fairly common in chemical reactions, is the carbocation, where carbon has 3 bonds and 0 lone pairs. Okay, so it has a formal charge of +1. This actually violates the octet rule, which is kind of bizarre. But again, it's not very stable. It's an intermediate in chemical reactions. Okay, so just like we had these like signatures that we were looking for oxygen and nitrogen, we have the same thing with carbon, where we can see if it has 4 bonds, check, then it's happy. It's got its complete octet. If it's got 3 bonds and a lone pair, it's got a -1 charge. And if it's got 3 bonds and no lone pairs, it has a +1 charge. Okay, cool. So the other thing with carbon, let's just draw a structure here. All right, just drew this random molecule here. We can classify carbons as either primary, secondary, tertiary, or quaternary. And leave myself on space. My handwriting's terrible. Okay, so we can classify carbons in a molecule as either primary, secondary, tertiary, or quaternary. And really what we're saying when we're classifying them as this is the number of carbons, they are bound to. Right, so how many carbon neighbors do they have? So a primary carbon would be one that only is bound to a single other carbon. So that would be like this one here. It's only bound to this one other carbon. A secondary carbon is one that's bound to two other carbons. So for example, this one here. Tertiary, I mean, hopefully you see where I'm going with this. Tertiary is a carbon that's bound to three other carbons. So that would be like that one there. And quaternary is bound to four other carbons. Okay, so everybody take a second and see if you can't spy me how many primary, right? I labeled one of them with my little red coloring here. There are other ones in there as well. See if you can't spot me all my primary carbons. Likewise, all my secondary carbons. All right, so everybody, let's do it in the chat. How many primary carbons do you think there are in this molecule that I drew? Yeah, cool. Right, so all these like endpoints here correspond to a primary carbon. They're all bound to just a single other carbon. Secondary, there would be two other ones in there, so for a total of three. Okay, you know, again, just to kind of stress, the big world of organic chemistry can be really intimidating. It's important to like keep things in context. Up until this point, we don't even know what this molecule does. We don't know anything about it. All we're really doing is being able to represent it in terms of drawing its structure and then talk a little bit about it, right? So what we just learned is we can sort of classify the carbons in a molecule as primary, secondary, tertiary, quaternary. We're going to see that this corresponds to like chemical reactions. Chemical reactions might want to take place at a secondary carbon, for example, but we're not quite there yet. Okay. So again, just to keep things categorized in your mind is kind of helpful in not getting intimidated by the course. All right. So again, today's kind of about like cleaning up some loose odds and ends about how we talk about our structures, things that we can learn just by looking at them. I do want to real quick go back to these electron pushing arrows. We talked about how we have chemical bonds. So this is an example here. And we can sort of describe reactions, right? So first of all, a chemical reaction is just the making and breaking of chemical bonds. Bonds are made of electrons, right? So what these electron pushing arrows are doing for us is showing how those electrons are flowing in a chemical reaction. So for example, here I have an acid-base reaction where I have, you know, if I'm gonna like write this a little bit more simply, I have a hydroxide ion reacting with ammonia to make water and the ammonium ion. So I have this hydrogen that's being transferred from this oxygen species over to this nitrogen species. All right, and that's exactly what my electron pushing arrows are showing. I have this one pair of electrons on the nitrogen that's like reaching out and grabbing that proton, that hydrogen. This is going to create this new bond that's formed, right? So again, when you think of these arrows, you think of, you know, you draw the base of your arrow, you think that you're reaching out and grabbing this pair of electrons and dragging them. So we can see that these lone pair of electrons on this nitrogen, this is what eventually became my new bond here, right? So I had a bonding pair of electrons, or something that started out as a bonding pair of electrons. I'm sorry, that's not it. Something that started out as a lone pair of electrons now becoming a bonding pair of electrons, right? So that's my new bond that's formed. And then I have this bond that's broken. And this formerly was a bonding pair of electrons and now jumps onto that oxygen atom, becoming this lone pair of electrons here. Okay, so these electron pushing arrows are a tough thing for an organic chemistry course. They're probably, they might be the first thing that was absolutely brand new information to you when we were introducing stuff last week. They are a little bit tough, but we like them because they explain how electrons flow in a reaction. So it's one thing to be able to say that these two reactants will create these two products. That's something we're going to learn over and over and over again, is which two things combine to make which two products, or one product, whatever it may be. And then these electron pushing arrows are now like this extra bit of information. They're that much more that we can talk about these chemical reactions, talking about how the electrons actually flow. Okay, so that's why we like them. We're going to learn a few different reactions, and for some of them, we're even going to learn the mechanism for them, how the electrons are flowing in that reaction. So that's why we care about this sort of stuff. Okay, I want to show a few other examples of these electron pushing arrows. Again, above we have this lone pair of electrons becoming a bonding pair of electrons. That's what's pictured in yellow here. That's as this new bond is being formed. Another thing that we're going to see is, for example, a reaction with a carbon-carbon double bond. Okay, an alkene. And so I guess just to be clear, because maybe we're not all experts at our bond line structures yet, this molecule that I've drawn above, let me actually draw the full out. All right, is the same thing as this molecule here. This is the structural formula, or the Lewis structure, and this is that bond line structure. So again, this is something that we learned last week. This carbon, or this endpoint here, represents that carbon. This one here represents this carbon, et cetera, et cetera. Endpoints and intersections represent carbons. And so what I've drawn here is in the middle is a carbon-carbon double bond. All right, so now I have 4 pairs of electrons that are being shared. That's what this is. Okay. We want to be good at our bond line structures, because again, it took me about 0.2 seconds to draw that bond line structure, and 30 seconds to draw the other one, which is again completely motivated by laziness. But organic chemistry is all about those structures, so we want to be able to draw those. Okay, so another example of using our electron pushing arrows is going to be starting at double bonds. So something like this. Okay, and actually I'll go, again, we get lazy and we don't draw our lone pairs. I'll do it for now. So first of all, this represents this bond breaking. And in particular, this pair of electrons that used to be in this bond have jumped onto that bromine, becoming now the bromide ion. So this pair of electrons here is now that lone pair on the bromide ion. Okay. What's different about this one that we haven't seen yet is this is another example of a bond formation. But previously, like in the example above, it used to be a lone pair of electrons and then became a bonding pair of electrons. Here, it's the second pair of electrons in a double bond, okay, what we would call a pi bonding electrons. And they reach out, and so this is going to form a new bond with that hydrogen. So for example, this. Okay, now this is not complete yet. There's something missing from this chemical equation here, and that is a charge. So one very important thing about charges is this idea of conservation of charges. So if you look at the example above, right? I have a positive charge on my left side. That means I have to have a positive charge on my right side. There's this conservation of charges that happens. Similarly to the example below, on my left side, I have the net charge is 0. Okay, so on the right side, my net charge also has to be 0. I have this bromide ion with this negative charge. That means that there's a positive charge missing. Okay, and that positive charge actually sits on this carbon right here. All right, now this might seem a little bit weird, so let's walk through this. I have what was formerly this pair of electrons here, now forming this new bond with hydrogen. That means that it's this pair of electrons here, right? Again, these electron pushing arrows are all about like watching the flow of electrons in these reactions. We don't even know why this reaction happens yet, right? We're just kind of following along based on the information given. So what I want you to kind of like convince yourselves of real quick is that this carbon here has that pair of electrons taken from it. It's got it snatched away, right? What was formerly that pair of electrons in that purple colored bond has been taken away from that particular carbon. That's why it's left with this positive charge over here. Okay, so when you have the breaking of this double bond like that, one of those carbons on either, I could have picked either side. I didn't really know beforehand, but one of those carbons is going to be left with a positive charge because it's having that pair of electrons taken from it. Okay, and so if we looked at this in our Lewis structure form, again, whoops. We have this, well, let me finish here. We have this pair of electrons that colored in purple above. I'll color it in purple down here. And it's apparently slightly different purple. Right? This has now formed this new carbon-hydrogen bond. That's what my arrows are showing. And now I have this carbon that I colored in blue that had that pair of electrons taken from it. So it's left with just 3 bonds and that positive formal charge. Okay. So this is the 2 types of bond formation that you'll see. Let me see if I can't zoom in. With our electron pushing arrows. One is a lone pair, electrons that started as a lone pair becoming a bonding pair of electrons. And the other one is electrons that started as a pi bond as the second in a double bond, becoming a new bonding pair of electrons. Okay, and then in both of these, you can see that the breaking of the bond is represented pretty much the same, where I start my base of my arrow at a bond, and then it jumps that pair of electrons onto an atom. In the above example, it's a oxygen, and in the below example, it's the bromine that's getting that pair of electrons. Cool. So I know that these electron pushing arrows are tough. They are, again, like an important part of the course because they say something really important, which is how electrons are flowing in a particular reaction, right? It is kind of like the hardest or the most extra piece of information that you could learn about a particular chemical reaction, but nonetheless, it's one of those things. All right. So one more thing with our arrows. I know that I'm beating these arrows to death. Up until now, I've been using this arrow with like what we would call like a double head, like a full triangle kind of thing. We also use these fishhook type arrows every once in a while where there's only one side to it. And let me explain why that is. It's 99.9% of the time you will use this type of arrow here. That's the vast majority of chemical reactions are with using that type of arrow here because this represents, whoops, a pair of electrons moving, whereas this only represents a single electron moving. All right. Again, 99.9% of the time, 99.9% of all reactions have to do with pairs of electrons that are moving. There is one particular type of reaction that has to do with single electrons moving, and it's going to be one of the first ones that we study, which are these radical reactions. So that's why we're going to make sure we know it. But again, they represent the movement of just a single electron. So let me actually draw. So this would be like diatomic chlorine gas. Chlorine has 3 lone pairs. Okay. There's something that happens with a chlorine molecule when you hit it with high radiation or high frequency light. So that's what this HV represents. It's not a V. What is it? A nu? I don't remember. Doesn't matter. Some Greek variable. It looks like an H and a V. That always represents light. Okay. So chlorine will actually react with light to form what's called a chlorine radical. And a radical has a single unbonded electron. All right, so it's not an electron pair. We almost always see our electrons in pairs. They like to be in pairs. There is this very special case scenario where you see an electron all by itself, and that is called a radical. It's called a radical just like the name implies because it's crazy. It's a highly reactive species. So these radicals are incredibly reactive. Those electrons don't like to be unpaired, basically. So when you see something like this, when you see that single electron, you think violence. That thing is crazy, all right? It's going to go sticking itself wherever it possibly can. So if I hit chlorine gas with light, it turns out that it forms these radicals because I have 2 chlorine molecule or 2 chlorine atoms in diatomic chlorine. I'll get 2 radicals out of it. That's what that 2's for. I don't want the times there. So I can show this happening using these fishhook arrows here. All right, I have this bond or this chlorine. Well, that used to be in this pair of electrons here. Right, again, I'm going to get 2 of these chlorine radicals out of this. To show the movement of this electron, use this single hook arrow to show that one electron's jumping onto that chlorine atom and the other electron is jumping onto that atom there. So there's kind of like bunny ears thing going on with these single arrows. That represents the movement of a single electron. So one electron is going one way, the other electron's going the other way. Again, super special case scenario to form these radicals, which are these highly reactive species. But actually, when we start talking about alkanes, our first functional group that we're going to learn, they're not really reactive molecules. And so the only thing that they really react with are these radicals here. So this is going to be something that we're going to hit like kind of first, even though it is, again, a rarity in terms of like all the chemical reactions that occur. Okay. Cool. So now we're going to talk. So first of all, any questions on that? I know that this stuff is a little bit bizarre. The other thing that I will say is, again, like nobody learns organic chemistry just by hearing somebody talk about it. It's all about when you start going through the problems, then you kind of realize. Please don't hesitate to reach out to me if you guys are struggling with anything. It does you no good to sit there and beat your head against the wall and not understand a particular problem. Reach out to me. Like oftentimes we can just work through it by email, but we can also jump on Zoom and I can share my screen, or you can share my screen, your screen, and show me what you're doing, et cetera, et cetera. Just let me know if we're stuck at any point with this. Okay. because I know that we're starting to get into brand new information here. So it's going to get a little tough. All right. So again, now just talking about we have molecules and we're trying to understand them. Let me draw an example. Yeah. So this structure here, actually, everybody take a second. And this structure here, convert this to one of these Lewis structures. Let's make sure we understand what we're looking at with this little structure, jaggedy line business here, right? How many carbons are there? What kind of bonds are there? How many hydrogens are there? Everybody take a second and draw me the Lewis structure or the structural formula for this particular molecule here. As you will find, it takes a lot longer to draw than the bond line structure, which is, again, the entire reason why we love these bond line structures. Everybody take a second and put in the chat what the formula is. So C what, H what? All right, what numbers go here? Yeah, cool. So I'm glad we're getting it here. So this is 1, 2, 3, 4, 5. There's only one here. 6, 7, 8. So this would be C4H8, right? So just being able to interpret these bond line structures is important because, again, you just kind of want to be able to look at it and sort of understand what's going on. That's going to take some practice for sure, but actually, if I were to draw this out with our Lewis structures, this would be the same thing. Okay. One other thing that we can learn from these structures is what we call hybridization. And why this matters is because it points to the shape of the molecule, right? So one thing that's kind of easy to forget when we're doing our pencil and paper organic chemistry is the fact that we're really talking about like these 3D shapes that these molecules have. And this needs to go away. Okay. So when we look at a molecule, we can tell what the hybridization of each of these carbons are, which points to the shape of the molecule. All right, so that's what we're going to learn how to do. To do that, you count what's called the number of electron regions, which is a fancy way of saying either the number of lone pairs or the bonds. And those bonds are of any order. So whether it's a double bond, a triple bond, a single bond, you always count that as just one electron region. And then there's this correspondence where ER, I'm saying electron regions. Actually, we could make this a little bit bigger. where the number of electron regions are going to correspond to the hybridization and thus to the shape of that molecule. All right, so if there's 4 electron regions, which is what carbon kind of like normally has, so that would be, for example, this carbon here, actually this one here as well. It's what we call sp3 hybridized. So depending on, I don't know, everybody's coming from a slightly different chemistry background. So hybridization could have been something that they 100% covered in 1A, or something that they kind of glossed over in 3A. You know, you might remember that we have these S and P orbitals. Essentially, they kind of like mix together to form these hybridized orbitals. Doesn't really matter. We don't need to know electron configurations. We do need to know how hybridization corresponds to the shape. And so the shape of these sp3 hybridized carbons are tetrahedral. Meaning they have a bond angle of 109.5. Okay, these are these tetrahedral shaped molecules. I will find a picture here in a second because it will help to see a 3D image. This is like one of those Vesper type of things. If you remember back to general chemistry, we only kind of need to touch on it a little bit, but let me just, again, sort of illustrate. I don't want you guys to get too bogged down in this orbital business. The bottom line is that, you know, we have these s orbitals and we have these p orbitals, and they'll mix together. They'll form a shape like this one here. Okay, this is what we call a tetrahedral. It's actually the way that you would space out evenly 4 things in 3 dimensions, is they space out into this kind of tetrahedral type shape. And the bond between any, or the angle between any 2 bonds is the exact same. It's 109.5. Okay. Going back to our little cheat sheet. If the number of electron regions is 3, as for example is the case with this carbon, because again, bonds of any order just count as 1 electron region. So we have 1 bond here. This would be the second one, and our electron regions. And then this double bond counts as a 3rd electron region. All right, so bonds of any order just count as 1 electron region. This is sp2 hybridized, so 1 less. And this forms a trigonal planar shape. So just to pick that word apart, trigonal, triangle, planar, meaning they all lie in the same plane. So it literally just looks like a 2D triangle, where the bonds are all 120 degrees apart. And so to picture that, oh, that's the tetrahedral again. All right, well, again, it looks like a triangle, so it would be something like this is a trigonal planar molecule, and all of those bonds are lying in the same plane. And again, it's shaped like a triangle here. All right, so then lastly, if the number of electron regions is 2, so an example of that would be a carbon-carbon triple bond. Right, and this just has 2 electron regions because I count this bond, and then this triple bond is just another additional electron region. So there's 2. This is sp hybridized, which is linear or has a bond angle of 180. Basically, in these triple bonds, these atoms are all just like lined up in a line, right? So just kind of exactly how it's written here. They're in this linear shape where they're all just run right after the other, perfectly 180 degrees apart. Okay, so I'm going to draw a molecule, and I want you guys to tell me what the hybridization is. And really, again, the whole reason we care about hybridization is because it corresponds directly to the shape of the molecule. And, you know, while hybridization sounds like it's this like extra piece of information, whatever, clearly we care about the shape of molecules in organic chemistry, right? They'll correspond to reactivity, all that sort of good stuff. Okay, so let's say that I have something like this. And again, since we're starting out, actually, the first thing I'd like you to do, because I really want to emphasize this, is to convert this molecule here into its bond line structure. Or no, I'm sorry, it is the bond line structure. Convert it into its Lewis structure. Make it its structural formula. Give me that. All right, and when you get it, go ahead and put the formula in the chat. Let's see who's got this. All right, so let me show you how I kind of go through and draw it, because I think sometimes it helps to just see like my thought process in this whole thing. Again, I'm going to go by doing the carbons first, right? I'm going to decorate the hydrogens after the fact. So the first thing I'm going to do is put that carbon backbone down. Starting from the end, I got 1, 2, so this is my first carbon, my second carbon, my third carbon, and now I come to this double bond. All right, so boom, boom, got a fourth carbon. Importantly, on either side of this triple bond is a carbon. All right, this one right here is really easy for people to forget about. I just see this, a mistake I see quite a lot here is to forget that there's a carbon at the base of that. So I'm gonna have one more single bond followed by my triple bond. Right, so that leads me to a total of 6 carbons. All right, so if you miscounted carbons, just real quick, go ahead and convince yourself that you see that there are in fact 1, 2, 3, 4, 5, 6 carbons there. All right, and now to go in and decorate with the hydrogens. Again, the whole idea is you're just completing the octet of these carbons. You're making sure that carbon has 4 bonds. So if it's got a double bond, it's only going to need 1 more hydrogen. This carbon here is already completely satisfied. It's already got its 4 bonds. So the last one is going to go on that carbon there. Okay, and given what we just learned, tell me what the hybridization on carbons A, B, and C are. Right? What's the shape of those molecules, or those carbons? Okay, so it's as simple as counting those electron regions. Carbon A has 1, 2, 3, 4 electron regions, meaning it's sp3 hybridized or a tetrahedral shape. Carbon 2 has 1, 2, 3 electron regions. Remember, I count that double bond as just a single electron region, meaning that it's sp2 hybridized or has a trigonal planar shape. And then my last one here has 1, 2 electron regions, meaning it's sp hybridized and has a linear shape. Right, so obviously, unless we're talking about a really simple molecule, you need to talk about the shape about each individual carbon. Right, so this is going to be this combination of some tetrahedrally shaped carbons and some trigonal planar shaped carbons and some linear carbons. All those combined will describe the shape of this molecule. Right, if it has more than 1 carbon, you got to talk about each one individually. Okay, but the shape is going to be something that's important. We'll see that it kind of corresponds to reactivity a little bit. Carbons that are easier to get to tend to be more reactive in a molecule. Okay, how much time? Not much. All right. So last thing we need to talk about, finish off this chapter. Again, probably a little bit of review, or at least hopefully, but maybe not so much. Okay, and real quick, this is obviously organic chemistry is in a series of courses. You have this prerequisite chemistry course that you guys would have had to have taken, right? The way that courses in general work is like I piggyback off of knowledge that you got in a particular course. But I understand that, like, I've been teaching second in a series quite a bit. Sometimes things don't ring a bell quite as much as they should, or that we assume that they do. And that's perfectly fine. But that just means you got to reach out and we can cover that gap, right? So we talked about resonance structures last time. Resonance structures are something that you went over in general chemistry, but probably promptly forgot about because it was a huge pain in the butt, right? That's cool. But if you do need to, we need extra practice with that sort of stuff, just let me know. I can guarantee you I have lecture videos, I have exercises, worksheets, stuff like that that can help fill in the gap. I've taught the whole spectrum of chemistry courses, right? So if there's anything that's from the past that you're missing, we can get that gap filled in pretty quickly, but you got to let me know, reach out for help. Okay. Last thing is polarity. We'll talk about bond polarity here. This is something that's particular to covalent bonds. So for example, if we have HCl, and this is really bond polarity is the result of an unequal distribution of electrons in a bond. right? So if we have something like a chlorine-chlorine single bond, this is what we call non-polar because the distribution is perfectly equal. So equal electron distribution. So if I like pictured the electrons in this molecule, it would be like this perfect little nugget thing, right? A perfect little oval where those electrons are all very equally distributed. In HCl, this is what we would call a polar bond because there's not this equal distribution of electrons. In fact, the vast majority of that electron density is actually sitting on that chlorine atom. Okay, so some elements like to hoard electron density in bonds. These are what we would call electronegative elements. All right, so some elements out there are just really greedy for electrons. They will hoard electron density in a bond if they are bonded with something that's less polar. And if we look at our periodic table, let's ignore all this stuff, sorry. The easiest way to remember what elements are electronegative is that everything points to fluorine. Fluorine is the most electronegative element. Anything that's bonded with fluorine, fluorine's going to be hoarding the vast majority of that electron density. Okay, so our trends for electronegativity tend towards fluorine. So either going across the periodic table or up. So these more electronegative elements over in this corner here will create these polar bonds. Cool. All right. So that's again something that we can sort of see looking at our structures here is whether or not a bond is polar, whether or not something's bound to something more electronegative. And yeah, so that's going to close it out for today, and we'll pick up next time. We'll actually start introducing our first organic functional group, the alkanes. These are like the simplest ones that just consist of carbon and hydrogen, like a lot of the examples we worked with today. And we'll talk about those functional, those types of molecules here. Cool. Oh yeah, good call. Let me get everybody punch your name in the chat. And then I'm done with you. Cool. All right. And please let me know if you're getting stuck on this homework or anything like that. I have office hours this evening, so that's a great place to show up and ask questions and all that good stuff.